So thanks, Bill. The stage is yours.
Okay, great. So does everyone hear me? Is it okay? Yeah, okay, we're good. So it's really fantastic to be able to talk to you guys virtually, and tell you about this very new paper, which I call quantum pseudo-entanglement. It's such new work that in fact it's not out on the archive yet. That's something we're going to remedy really quickly, but I never promise exactly dates on these things. But it should be out pretty soon. And this is based on joint work with my collaborators, Adam Boland, Shomik Ghosh, Umesh Vazirani, and Jack Zhou. Okay, so the starting point for this talk, as I think all of us can agree, is that quantum entanglement is a really subtle notion. I think it's fair to say we really don't understand it completely yet. One way to see this immediately is we can look at this illustration from the Nobel Prize citation, and this last year, and from my perspective, it looks like we have two quantum particles that have been attacked by a series of small worms. Right. So clearly this is a very subtle concept, something I think it's fair to say we don't understand. But from the perspective of quantum computation, we know that some of it is necessary for non-trivial quantum speedups. But on the other hand, it seems like we don't need that much quantum entanglement to be hard to simulate. Even we have good examples of quantum computations that produce a reasonably small amount of entanglement that can still be hard to classically simulate. But at the same time, it seems like it's not, a more the merrier situation. We have examples of quantum states with really high entanglement that are in some, formal sense useless for quantum computation. So I think, again, it's fair to say that we don't understand exactly the role that entanglement plays in, enabling quantum computational speedups. And in this work, I'd love to tell you that we've solved this problem, but instead, I fear we're going to muddy the waters even worse. We're going to talk about what I think is a new property of quantum entanglement, which is that it's not sort of a feelable property. And what do I mean by that? Well, what I mean is that it can't be, efficiently observed. In other words, we'll construct two explicit ensembles of quantum states, one that have very low entanglement and one that has very high entanglement, with the property that no efficient quantum algorithm can distinguish these two states, even if we give that algorithm a large number of copies, like an arbitrary polynomial number of copies. So this is something that was not known before, and we're pretty excited about it. Let me also pause before I go on just to say I would love to have questions during the talk. So please don't wait for me to get to a certain stopping point. I'd love for this to be a conversation. Okay, so let me keep going. So we're going to talk about entanglement in the context of random quantum states. And we know, of course, that random quantum states drawn from the Haar measure, n qubits states from the Haar measure are really important resource. If we could somehow get our hands on a truly Haar-random quantum state, we would be in a great place. There would be lots of things we could do with it. But unfortunately, truly Haar-random states are of a limited use from a computational point of view. And that's because by very simple counting arguments, they tells us that we need exponential sized circuits to approximately prepare most quantum states from say a simple state like all zeros. So there's just not going to be a computational way of accessing most quantum states on n qubits. It just doesn't exist. So nonetheless, though, we can get over this by considering what's, I think, now a very central concept in quantum information, just what we call pseudo-random ensembles of quantum states. These are, by construction, quantum states that are efficiently preparable. But therefore they're clearly not Haar-random, because Haar-random states with high probability do not have polynomial, size quantum circuits. But they, but even though they're not truly random, they mimic certain important properties of truly random quantum states. Until very recently, most of the pseudo-randomness notions that we've been studying as a quantum information theory community have been sort of information theoretic. So For example, there's this object called a quantum state T design, which is, roughly speaking, it's an ensemble of quantum states with the property that, no algorithm, no matter what running time, can distinguish at most T copies of a state drawn from this ensemble from T copies of a truly Haar-random quantum state. So this is what we call a quantum T design. Sometimes a quantum T design refers to a unitary, pseudorandom unitary. So for me, it's just going to be an ensemble of states, but they're, clearly related concepts. And this notion of quantum T design is now a very central topic in quantum information theory, with many important applications. For example, to randomized benchmarking, where maybe we want to understand our error rate of some 2-qubit gate that we implement experimentally, and we want to know how good of a job we're doing. How close to the true gate did we just implement? And it turns out that quantum 2 designs help us do this in sort of a sample efficient manner, which is pretty awesome. Quantum advantage experiments. This is something, I think a lot about in my group. The sort of state-of-the-art quantum advantage experiments involve implementing what's called a random quantum circuit on some number of qubits, like 53 qubits in the recent, the famous Google experiment. These are not by any means, truly Haar-random unitaries that act on 53 qubits. That would be some ridiculously large, indescribable 2 to the 53 by 2 to the 53 matrix. Instead, there's some approximation of like a quantum 2 design. Okay. And then even quantum gravity and notions of holography, which are really important from from the point of view of quantum physics and gravitation. It's become sort of fashionable and I think useful to sort of have a toy model for the dynamics of a black hole described by a quantum 2 design. So it turns out that there are sort of information theoretic similarities between how we expect a black hole to act and quantum 2 designs, namely that they have this sort of notion that they scramble information in a certain formal sense. So this has been very, very successful theory, but from a computer science perspective, what's sort of strange, I think, is that in computer science, pseudorandomness is equally as important as it is in quantum information theory, maybe even more important, in the sense that it's really been one of the most central topics in complexity theory for 30 years at least. But what's funny is that in computer science, we generally talk about a sort of orthogonal notion of pseudorandomness, which I'll call computational pseudorandomness, as opposed to information theoretic pseudorandomness. Now, generally, when we talk about computer science and pseudorandomness, we're talking about classical objects like distributions over bit strings and things like that. But to be consistent with the the previous slide where we introduced T designs, I'll sort of introduce what it would mean for a quantum state to be computationally pseudorandom. What I mean is it's some sort of ensemble of quantum states, X over, say, n qubit states, with the property that this ensemble is not, truly Haar-random. But, from the perspective of an efficient quantum algorithm, which I'm calling A here, it's just as good in some sense, in that, no efficient algorithm A can distinguish these states from truly Haar-random states, even if we give the algorithm A an arbitrary polynomial number of copies. Okay, and so this is what we say formally. We're sort of challenging the algorithm to output something different if it thinks it had a state distributed from X as opposed to a state distributed from Haar. And we're sort of enforcing that for all algorithms A, there's no algorithm that can make this distinction with any probability that's sufficiently large, like any polynomial probability, 1 over polynomial. Okay. Now, unlike T designs, which we have sort of unconditional examples of T designs, without meeting any sort of hardness assumption, in general in computational pseudorandomness, we give that up, and it requires complexity assumptions. So, for example, in the case of quantum pseudorandom states, this requires actually, it shouldn't say requires. It seems to the current constructions need the existence of one-way functions that are secure against quantum computations. It's a pretty standard assumption. In other words, it's saying as long as cryptography is possible in a quantum world, so are these ensembles of pseudorandom quantum states. But at least in the classical notion, even though we give up this sort of unconditional security, this notion has been super useful and has enabled a wide variety of applications that are simply not known or even expected to be possible in the information theoretic setting where the adversary is, completely unbounded, like, public key cryptography, homomorphic encryption, de-randomization of, bounded error, probabilistic algorithms, all of these things, are sort of really nice, really useful applications of computational notions of pseudorandomness, but, as a consequence, do require some sort of hardness assumption.
Bill, if you're waiving off the limitation on the number of copies, but still require the algorithm to run in polynomial time, does this become degenerate in some sense?
Well, I don't know about degenerate. I mean, what I would say is you can definitely consider sort of hybrid notions, right, of the two things. I think that's sort of what you're saying. One thing that would be disappointing about that from my perspective, though, it's not really that it's degenerate and it doesn't mean anything. It's more, I think you can define it. It's more that, we actually have pretty good constructions of T-designs, right? And T-designs are like a much stronger notion than what you just described, right? So in other words, they, if T is some fixed polynomial, for example, like n squared, we actually have, n squared designs that would have not only the property that you're talking about, but in fact, the property that that no algorithm whatsoever, efficient or not, can distinguish it from a Haar-random. So that's why I introduced this concept. I think when this is really at its most powerful, it's when we consider sort of an arbitrary polynomial number of copies. Did that answer the question, or do you have something else in mind?
I guess I'm trying to understand. I mean, if the algorithm is running in polynomial time, then it can only, measure or access, polynomial number of copies, unless you're doing something, maybe more. So I'm trying to understand whether there is anything that can be done more sophisticated, which is.
Oh, sorry, are you asking about like maybe more than polynomial number of copies? Or I mean,
Yes,
clearly that
yes.
Oh, sorry, yeah, clearly unless I define something in a strange way, you're not going to be able to say anything about super polynomial number of copies of the state, right? Because you have a polynomial time distinguisher.
Okay, fair enough. Thanks.
Yeah. You'd have to define what you mean by that, to talk about super polynomial copies. So for us, it's always going to be polynomial. This is really the strongest notion in terms of number of copies that you can expect because you have polynomial time. So you simply can't access super polynomial number of copies of a state with this distinguisher. But I think maybe it's a good point. I would like to sort of be very clear about the differences one more time between these computational notions of pseudorandomness and T-designs, because they really are incomparable notions. On the one hand, here for these computational notions, we're making a restriction that the quantum algorithm is efficient, which we don't do for, say, a T-design. But then we're dropping the restriction that we only have, say, T copies of the state, and for these computational notions, we can have some arbitrary polynomial copies. So we're really only bounded by the runtime. So they're really sort of apples and oranges. I don't think there's an obvious way to compare them. Maybe it's a good point to take any other questions before I go on into sort of more advanced things. Happy to give it a second. Okay, so why don't I keep going then? So, our interest in this talk is going to be on the relationship between pseudorandomness on the one hand and entanglement. And it's one thing that we've known for many years now is that most Haar-random quantum states are essentially as entangled as they come. And what this means, roughly speaking, is that, if you consider dividing the n-qubit state into, some partition of the qubits, so like n over 2 qubits A and, subsystem A and a subsystem B on the rest of the n over 2 qubits, it's essentially maximally entangled. You have essentially n entanglement entropy n. You can ask, is this also inherited by quantum t-designs? And it turns out this is true. It's a little bit more subtle, and the proof is not as it hasn't been known for as long. But it turns out that quantum t-designs are also essentially maximally entangled. So you can prove results like that say things like the expected entanglement entropy of a state drawn from a quantum t-design is essentially linear across any bipartition for any t greater than 2. So this is an expectation result. You can actually prove stronger results in terms of concentration that say something like this, with very high probability, in fact, with probability that gets very, very close to 1 as t increases, a state drawn from a t design has a linear amount of entanglement. But I think what's really surprising about our result, and it's not something we expected. It's one of these results where I didn't really have a lot of intuition either way, but we're actually going to show that computational notions of pseudorandomness need not be so entangled. So in fact, you can get away with a lot smaller entanglement if you're willing to have a computational notion of pseudorandomness as compared with these information theoretic notions. Okay, cool. So to describe, what we've done, let me take you back to, the original construction of a pseudorandom quantum state from 2018. So this is, I'm giving this sort of credit to two people, to Liu and Song. This is this JLS 18 paper, and then a follow-up paper in 2019 by Brzezinski and Shmueli. The results I'm going to present are some mixture of the two, but the original construction is pretty close to what was identified in this JLS paper. So what they do is they consider states of the following form, which we'll call psi sub fk, where fk is any quantum pseudo-random function. So roughly speaking, what that means, if you're not familiar with cryptography, is that there's some key, which is some classical information k, and if we know what that key is, then we can compute f sub k. But if we don't know what that key is, and to us it looks uniformly random, then we can't distinguish fk from a totally random function with anything fewer than some super polynomial number of queries. Okay, and so these are the states that they're considering. They look like the uniform superposition in the sense that the magnitudes are all uniform, like 1 over square root 2 to the n of each of the amplitudes. But the binary phase of the amplitude, or the sign, is specified by this quantum secure pseudorandom function. And the main result of this line of work is that this ensemble of states, it's an ensemble because we think of k as a parameter that varies, that's a computational pseudorandom state. In other words, it's a PRS ensemble, assuming that quantum secure cryptography is possible. Essentially, you can get this under any assumption that would give you the existence of a quantum secure pseudorandom function, including, for example, the existence of a one-way function secure against quantum attacks. So essentially, as long as modern cryptography in any form is possible in quantum computation, we have these pseudo-random ensembles of quantum states.
And Dave, how does the size of the ensemble k scales with respect to n?
Yeah, good. That's actually a good question. We can always think about it as an efficient parameter, right? It's like some polynomial, or even smaller, in fact. But for us, we can think about it as a polynomial. It's nothing. You're not going to lose anything there. Okay, and so to be really formal, this means two things: the fact that it's a computational pseudo-random state. One, that if you give me the key, we can prepare the state efficiently with a quantum computer. But two, if we don't know the key, so this is very similar to how I defined a PRF. If we don't know what the key is, then no efficient or polynomial time quantum algorithm can distinguish polynomial number of copies of psi sub fk from copies of a Haar-random state. So this is the same thing we talked about before. This is what we mean by computational pseudo-randomness. Okay, great. Any questions about the definition? Okay, great. So I'll keep going.
Sorry, I have a very basic question.
Yeah.
So I'm not very familiar with this stuff.
Yeah.
And just a really simple one to start off with. psi fk, it just has like plus or minus signs. No,
Yeah.
sorry, never mind. I think I've so it's an equal distribution of each states, whereas I'm assuming is a Haar-random state, does all the amplitudes have the same size in that?
Oh, definitely not. Definitely not. Right. In a Haar-random
Yeah.
state, it's true that there's some sort of concentration property. So it's, you can say that most of the amplitudes are have some similar magnitude or
Yeah.
something like that, but it definitely doesn't look like this. Just as you described, this is very much like a uniform superposition, but where only the phases, only the signs change. So they call this a binary phase state for sort of obvious reasons, because the phase is just a binary. It's a plus or minus.
And I guess couldn't you just like measure and notice everything's kind of equally distributed in this state, whereas the chance of a Haar-random state having like equal amplitudes is really small.
Right. It's a great question. I mean, what I would say is you might have thought that something like that is true, and what they're proving is it's not. Right. As long as you believe in cryptography. I mean, the one thing I would say is that clearly there are sort of degenerate cases of this that would be distinguishable. Like, for example, if you get really unlucky or horribly unlucky and you get like all positive, right? Well, then you can clearly tell that apart. You literally have a uniform superposition. But of course, that's not the case. This function is with extraordinarily high probability, sort of has a mix of signs. And what this is saying is, at the end of the day, there's no computational way of telling apart this sort of ensemble of state from a truly Haar-random state. And it's not obvious, though. Like, I think that was somewhat surprising. In fact, the original construction, now that you asked, the original JLS construction, it didn't just have a binary phase. It had like a k-ary phase. This was like a root of unity, like omega k raised to some power, and then this pseudo-random function was not plus minus one mapping, but was mapping to plus minus k. And it wasn't really clear until Brikursky and Shmueli that in fact we didn't even need that we can just have binary phase. Good question though. Any others? Okay, fantastic. So let me keep going. Okay, how entangled is this JLS ensemble? So JLS ensemble, that's the the names of the guys who made it. That's the same ensemble that we just described with this binary phase. Well, they have one result about this, which is the following, and this comes from their original paper in 2018. They say, let's say you have a reduced density matrix of psi sub fk on any subsystem A. Then what they can show is the entanglement entropy with respect to that density matrix is strictly greater than log n with high probability. So this gives a lower bound for the entanglement entropy of these states. And the proof is really simple. So I thought I would sketch it. It's just a very simple lemma, which is that the trace of rho squared has to be strictly less than any 1 over polynomial quantity with high probability. The reason is because if this is not the case, if the trace of rho squared happened to be greater than or equal to 1 over n to the c for some constant c, well then there actually would be a very simple distinguisher from uniform, which would be just the swap test. So what you do is you literally take two copies of these states, psi sub fk, and then you apply the swap test on subsystem A of the two copies, and the claim is that this would be an efficient distinguisher that would distinguish psi sub fk from a Haar-random state. And the reason for that is because for a Haar-random state, this trace of rho squared we know to be inverse exponential with extremely high probability. And so if the trace was much larger than that for this psi sub fk state, then we could distinguish this, right? Because if the swap test ever accepts, right, we know that it essentially has to be this psi sub fk state, right? So this would be a good distinguisher if it was not for the case that the trace of rho squared has to be less than 1 over n to the c for all c. And from here, once you get that, the lower bound on the entanglement entropy directly follows from this lemma. by a simple consequence of Jensen's inequality. Jensen's inequality tells us that the entanglement entropy of a reduced density matrix rho is greater than or equal to minus log of trace rho squared. And so you plug this in, and what you get is that the entanglement entropy has to be strictly greater than log n. So this was the only thing we knew until very recently, until our work, that the entanglement entropy of these pseudorandom states has to be greater than log. Any questions about this proof? You've seen the swap test before, I sort of assume. I'm happy to describe it if you'd like to go into that. Sorry, I'm not sure I'm hearing. Are you saying something?
Is that better?
Yeah, that's much better.
Okay.
Sorry, I was seeing your mouth, but I didn't. Yeah.
It was something complicated. I was actually just far away from it. We have a one over n to the c.
Oops, now I can't hear you again. I think we're having some technical difficulty with
Okay.
the mic.
Is that better?
Yeah,
Okay.
it's temporarily at least much better.
I think I have to look at my computer to talk. That's very strange. Okay. As you take c very large in this trace of rho squared is less than 1 over n to the c.
Yeah.
Does that not say that trace of rho squared is then equal to 0? Or is some kind of...
No. So yeah. Sorry, I should be really clear. I'm talking about constant c, right? So c, I'm thinking about this asymptotic limit where c doesn't depend on n.
Okay, so for fixed c at some point for n large enough, it has to be less than n.
That's what I'm saying. Exactly. So c is fixed, n is growing. Yeah, absolutely. I mean, this is really, I just wanted to write this as less than 1 over poly for any poly.
Okay, thank you.
Yeah.
Could you go over the swap test, please?
Yeah, of course. So the idea with the swap test is that it's sort of a particular test that of two pure states, and in this case we're using it more generally, but in general you can think about it as two pure states, psi and psi prime, and it's the success probability of the test is directly proportional to the overlap, the inner product of psi and psi prime, and it's not so hard to see what that test is. I'll maybe, rather than sort of going into detail, it's essentially like a controlled swap operation. You can look at the circuit on Wikipedia. Sort of uses a control bit, and you sort of Hadamard it, and then you swap, and then you Hadamard that control bit again. But I think for the purposes of this talk, what's really important is that it gives a way of taking two states, and when we measure a control qubit, outputting 1 if with a probability proportional to the overlap of those two states. Does that help out?
Yes, thank you.
All right, great. So let me keep going. So this gave a lower bound, but we didn't have any previously known upper bound on entanglement. In other words, we didn't have an example of a pseudo-random function f, so that the corresponding binary phase state psi of fk had saturated this entanglement entropy of log, of greater than log until now. And so this is what we show. We show how to make a low entanglement pseudo-random state ensemble. And so to do this, we're going to consider the JLS construction, the same thing we just talked about, but we're going to divide the n qubits in half, and we're going to denote the subsystems A and B. So A is going to be over n over 2 qubits, B is going to be over the other n over 2 qubits. And we're just going to write this JLS construction, I'm dropping the K here just for convenience, as psi sub f, which is exactly like this. I'm just rewriting what I had before, but I'm dividing the qubits into two partitions, and I'm thinking of the function as, instead of as a function of n, from n bits to plus minus 1, it's just from n over 2 plus n over 2 bits to plus minus 1. So I didn't do anything, to be clear. I just rewrote this, okay? And for convenience, we're going to think of this state as encoded by a pseudo-random matrix, which we'll call CF. CF is just the matrix whose ijth entry is equal to Fij. Okay, so it's sort of encoding the truth table of this PRF. In other words, more formally, CF is this 2 to the n over 2 by 2 to the n over 2 matrix whose rows are indexed by basis vectors of subsystem A and whose columns are indexed by basis vectors of subsystem B. And so this is really just another way of directly encoding this state, this binary phase state. But the reason it's convenient is because it turns out that it's not hard to see that the reduced density matrix of the state on subsystem A, so if we trace out the n over 2 qubits, I'll call that reduced density matrix rho, and it can be written directly in terms of the of this matrix CF. So it turns out it's CF times CF transpose. So the point is, by studying properties of this matrix F, of this matrix CF, we can understand properties of this reduced density matrix. So it's convenient for us to think about this state as this pseudo-random matrix. Okay. So any questions about that before I move on?
Sorry, where does the 1 over 2 to the n come from in this expression?
Oh, that's just the normalization. I mean, you can see that here because there's this state I didn't normalize, right? This f of
of course, yeah.
plus minus 1, and yeah.
Okay,
yeah.
thanks.
Yeah, that's a good question. Okay, great. So let's keep going. So what are we going to do? Well, our goal is to minimize the entanglement entropy of this reduced density matrix, S of rho, which I'm just rewriting as S of 1 over 2 to the n times CF transpose. Now, here's the big picture idea, which is actually really simple. I'm going to describe it very informally here, and I'm going to describe it formally in the next slide. Suppose we pick a small subset of the rows of this matrix CF and build a new matrix, which I'll call CF prime, which has the same dimension, for which each row in this new matrix for which each row in this old matrix CF is repeated many times in this new rate matrix CF prime. So for example, if this is CF, right, we might consider taking the first row of CF and repeating it 3 times in CF prime. Then maybe we take some other row in CF prime and repeat it 3 more times, something like that. Right, so this is a really simple way of reducing the rank of this matrix CF, right? The rank can only go down when we do this. And so the point is, we think about this new matrix CF prime, the one that has repeated rows, as encoding a new binary phase state, which I'll call psi prime sub f, right? In which the binary phases are encoded by this new matrix with repeated rows. And the point is that this has reduced rank, and so the corresponding reduced density matrix, if we trace out the last n over 2 qubits, will have lower entanglement entropy. That's because of Jensen's inequality. We'll formalize that in a moment, but there's a very explicit connection between rank on the one hand of the reduced density matrix and entanglement entropy. Okay, so that's the very, very high level idea. Of course, I haven't formalized what it means, and I'll do that in a moment, but the basic idea, okay?
Just to get a rough feeling, what is small subset roughly, and then how many repetitions?
Yeah, sorry. We'll yes, we'll get to that in a moment. That's of course really, really important. But that's what I mean when I say we're not being formal at all. We'll answer all of those questions in like the next 2 slides.
And is it crucial to choose the subset at random, or it could be an arbitrary?
No. No. We'll talk about exactly how we choose the subset. I don't want to get into it because I'll say in such detail in a moment that I think it will be very clear.
I'll wait patiently.
Yeah. So just give me a second. If it's still not clear, let me know. So here's the construction. Let's be a little bit more formal. So how do we select the subset of repeated rows? So what we're going to do is we're going to consider the rows of this new matrix with the rows of this new matrix, which came from repeated rows of the old matrix, CF. We're going to think about it as specified by a 2 to the L to 1 function, which in fact we'll construct explicitly in a moment, which we'll call G. And what it means to be 2 to the K to 1 is just that for every Y, the size of the preimage G inverse of Y is either 2 to the L or it's 0, okay? Now, let me give an example. I think it's easiest to specify by example how we're going to use G to specify the rows of this new matrix C prime. So for example, let's think about L equal 1. So then G would be a 2-to-1 function, right? So maybe a G looks something like this. This is the domain. This is the codomain, right? And we're going to think about the domain of the function G as sort of encoding the rows of this new function, of this new matrix CF prime, and the codomain of G as specifying the rows of the old matrix CF. So in this simple example, for instance, we'd have that the first row of the new matrix CF prime is the same as the first row of the old matrix CF, and then the second row of the new matrix CF prime is the same as the first row of the old matrix, and so on. Or to say it more formally, we define CF prime to be the matrix whose ijth entry is equal to the gijth entry of CF, the old matrix. Okay. And so the point here is that the rank has been very much decreased, right? The rank of the new density, reduced density matrix, if we trace out, n over 2 qubits in this new state, that's equal to the rank of CF times C prime F times C prime F transpose, which by properties of rank is equal to the rank of C prime F. And the point is that's less than, it has to be less than or equal to 2 to the n over 2 minus L. The reason for that is because this is the number of distinct rows in the repeated, in the new matrix CF prime, right? So that gives us an upper bound on the rank. Okay, now we still haven't answered Tom's question because of course I haven't told you how to construct this function G or how we should choose L, right? But other than that, any questions about what I'm talking about? All right, so let's do that. Sorry, I maybe I didn't quite finish. So by Jensen's inequality now, what it tells you is that the entanglement entropy of this new density matrix rho prime less than or equal to log of the rank of rho prime. And so for us, it means it's less than or equal to n over 2 minus L. Okay, cool. So we're not done. And one of the reasons we're not done is because we simply haven't specified the construction. But another reason is because, all we've done so far is given sort of a recipe for how to take a state with a certain amount of entanglement and reduce its entanglement. But we're not, that's not what we're trying to show. We're trying to show not only that the new state has reduced entanglement, but that we can't distinguish the new state from the old state, right? That you have a security notion, that it's computationally, these two states are computationally indistinguishable from each other. And so what we're going to ask is, can we distinguish this reduction of rank with a quantum algorithm that gets an arbitrary polynomial number of copies of either state? And so the way we're going to prove that you cannot do this with an efficient quantum algorithm is to consider a very specific construction of a 2 to the L to 1 function, which we'll call G. So the G we'll consider, and that's the function that encodes the repeated rows of this new matrix CF prime, is the composition of 2 quantum secure pseudorandom permutations. But then the second one will mod by 2 to the n over 2 minus L. So this is a pretty standard way of getting a 2 to the L to 1 function. And we're going to argue that we can't distinguish this new matrix with a lot of repeated rows from a truly random matrix by arguing about 2 steps. And I should say these 2 steps, I'm skimming over a lot of the details. So this is just a high level picture, but there's sort of 2 steps. The first we call hybrid 1. We show that this new construction is this new matrix is computationally indistinguishable from a truly random matrix instead of a pseudo-random matrix with, so we'll call that R, with repeated rows selected by G. So in other words, this matrix, which started with a pseudo-random matrix CF and then repeated rows, is indistinguishable from a truly random matrix, truly random plus minus 1 matrix with repeated rows selected by the same pseudo-random function G. And that's not so hard to see. It's essentially the high-level idea, even though it's actually a little technical to show this, is that this is true because by construction we chose CF to be a pseudo-random matrix. So it's computationally indistinguishable from a truly random matrix by construction. And then what's sort of complicated to show is you have to show that everything works even when you compose things Even when you think about repeating the rows of this construction. So then the second hybrid shows that this new matrix, the one that we talked about in hybrid 1, is computationally indistinguishable from a truly random matrix R whose repeated rows are selected by a truly random permutation, right? And the point of that, of course, is that if we take a truly random ±1 matrix, and we repeat its rows according to a truly random permutation. In fact, it's not really repeated, it's just permuted, right? Well, then this is equivalent to a random matrix. We just took a random matrix and we, interchanged its rows. And what we can show, so this is equivalent, just statistically to a truly random matrix. And so the proof that this is secure, that these two hybrids are indistinguishable from each other, in fact, follows from a complicated argument that bottoms out on the collision bound, saying that you can't distinguish G from a truly random permutation. So even though G is a 2 to the L to 1 function, so it has a lot of collisions, right? You can't see these collisions as long as L is as large as n over 2 minus log squared n, right? So one thing I want to say is that this is essentially tight, because if it was like n over 2 minus log, right, there would be like only a polynomial number of distinct rows in this repeated matrix, right? And that you can easily distinguish by just like querying rows at random and seeing how many of them are the same. But in this case, when you have L as large as n over 2 minus log squared, you have a quasi polynomial number of distinct rows, and so this sort of attack doesn't work. And in fact, this is saying that no attack would work. This is in fact this new matrix, which has a bunch of repeated rows, is in fact indistinguishable computationally from a truly random matrix. All right, this is there's a lot of technical details that I'm clearly brushing under the rug here, but let me just pause for a moment and just ask if there's any sort of questions about this construction or how it works or what I mean by something. Okay, let me just continue, and of course you can always ask questions at the end. So what have we done, right? Well, we've shown that this new matrix with repeated rows is a pseudo-random matrix, but it has really small rank. So it has rank 2 to the n over 2 minus L, where L is equal to n over 2 minus log squared n, so that the n over 2's cancel and you get 2 to the log squared n. Correspondingly, this state, which is encoded by this new matrix with repeated rows, is just the binary phase state that comes from this matrix C sub f prime. It's a PRF using arguments of JLS. Why is that? Because what we've essentially done, if you're sort of following along, is shown that the entries of C sub f prime are like the truth table of a new pseudo-random function. It's essentially what we proved. And therefore, we know that if we have the binary phase state construction, which is specified by a pseudo-random function, that's a computationally pseudo-random ensemble of quantum states. But yet the entanglement entropy is upper bounded by log squared n, which again is pretty exciting because that's it's very different from the maximal entanglement, essentially n entanglement that we see in quantum T designs. Okay.
And does it match what we get from the swap test?
Yes, it does. Yeah, it does actually. It's completely consistent with the swap test, because what the swap test is telling us is that the entanglement entropy needs to be strictly greater than log.
All right, so there's still like
oh, not really, because we didn't. No. Right. I just said log squared. What I meant is like little omega of log. Like anything greater than log would be fine.
I see.
So yeah, it's perfectly matching. I just wanted to be more simple, so I said log squared.
Sure.
Bill,
Yeah.
is it so you have like low entanglement of across this like AB bipartition? Is it possible to get low entanglement across every bipartition?
That's a fantastic question. That's exactly what we're currently working on. We don't
okay.
we don't actually know right now. We have ideas to extend this so that it's not it's not about just a single bipartition, but at the moment we haven't been able to extend this to a large number of bipartitions, and it's very much sort of our our current interest, in fact. It's a great question. The one thing I want to say, though, is that even though you can say, okay, well, you're only talking about a single fixed bipartition, for these other notions, like, for a truly random state or for a quantum T design, it does not have this property. It really is the case that every partition would have to be maximally entangled. So in that sense, I think it's interesting to talk about a single partition. But of course, you could also ask stronger questions, like, could it be that for many other sort of ways of partitioning the state into A and B subsystems, you still have low entanglement? We don't know that, strictly speaking.
Thanks.
Yeah, sure. That's a really good
Can I
question.
ask if my sorry. Can I ask
Yeah,
why does this not work if you replace log squared m with log m?
Yeah, that's what I just said. So it doesn't work if you replace log squared with log n, because then if you really think about what's going on, you've repeated so many rows in your new matrix C, C prime sub f, that you actually have only a polynomial number of distinct rows, right? That's an easy calculation to see. It's like 2 to the O of log, right? That's the number of distinct rows, essentially. Now, if you have a matrix that has a polynomial number of distinct rows, right? Well, then there are kind of straightforward strategies for distinguishing that from a random matrix that wouldn't have repeated rows. For then, the thing that should come to mind is that you kind of query a polynomial number of rows in the matrix, right? And you sort of see what they are, and you have a very large chance of getting a collision in that case. So this is really as good as we can hope for. Awesome. Let me keep going because I'm running out of time. I wanted to say that we can extend this to a PRS with tunable entanglement. Let me say what I mean by that. So far what we've done is it seems like we've taken like some, PRS that has potentially very high entanglement. We don't really know, but whatever it is, and sort of reduce the entanglement. But in fact, we can extend this so that we can construct a PRS with respect to, again, some fixed partition of the qubits, so that the corresponding, entanglement entropy is exactly equal to k. It's upper bounded and lower bounded by k for any k between like log squared and n. Okay, we didn't have that with the prior construction, essentially because we never talked about how much entanglement we started with in the first place in that first construction. We just said take a pseudorandom matrix, right, which came from the JLS construction. We didn't say how much entanglement that had. It could have had any amount of entanglement, and we said let's reduce it. Right. But if we want to get this sort of tunable entanglement, we need to start with a binary phase state, right? So that the corresponding the entanglement entropy is large, and we know exactly what it is. Like it's like a linear quantity. So that's and then the idea is once you have that, once you know how much entanglement exactly you started with, in particular a lower bound on how much entanglement you started with, then you can use the same idea that we had before, with a 2 to the L to 1 function that sort of reduces the rank by repeating rows. By choosing L carefully, you can get an exactly matching upper and lower bound on entanglement. So that's the idea. Let me see. I feel like I'm going to run out of time, so I'm not going to tell you about this high entanglement construction. You can read about that when our paper comes out. But I want to tell you about what I mean by pseudo-entanglement, because as I was describing to some people earlier in this talk, it's not every day that you get to define something, a term with, especially a one-word term like this that I keep getting spelling mistakes on and spelling corrections on and so on. So what do I mean by it? So what I mean by pseudo-entanglement is something like this. There's two ensembles of n qubit states that are indexed by a secret key k. And we call them F and G pseudo-entangled if, given the key, these two states are efficiently preparable by a quantum algorithm. But then if we're not given the key, and the key looks uniformly random to us, then the ensembles are computationally indistinguishable from each other. But on the other hand, the entanglement entropy between the first n over 2 qubits and the second n over 2 qubits of these two states, is on the one hand, for one of the ensembles is like exactly like, upper bounded and lower bounded by f of n, whereas with high probability for the other ensemble, it's upper bounded, lower bounded by g of n. And so what's interesting is, when we started thinking about this, it turns out we were not the first people to observe this, but we were the first people to name it. But actually, the concept had been thought of before implicitly in some work by Gheorghiu and Hoban from 2020. They don't talk about it this way, but it turns out what their main result can be summarized by saying, assuming learning with errors is secure against quantum attack, which is like a particular cryptographic assumption, then there exist n and n minus O of 1 pseudo-entangled states. Okay. Whereas, but what's interesting about these states when we looked into it is that in fact, neither one of these states are computationally pseudo-random. So it's sort of interesting, they're indistinguishable from each other, and they have very different entanglement spectra, entanglement entropies. But in fact, they're both distinguishable from Haar. So they're not ensembles of pseudo-random states. And so we can think of our result as sort of strengthening this main result, which we're weakening the assumption. We're saying not only can we get this from LWE being secure, but assuming any one-way function is secure against quantum attack, then there are n and log squared n pseudo-entangled states. So our gap is much bigger. And as a bonus, we also get computational indistinguishability from Haar-random, whereas this was not the case in the previous work. And it's actually kind of a fun exercise to look at their ensemble of states and to see why it's distinguishable from Haar. It has something to do with the fact that LWE has a certain linear structure because it has to do with, a noisy system of linear equations. And it turns out there's a pretty simple distinguisher that allows you to make use of that structure to distinguish these states from Haar-random. Okay. Then we talk about some applications. The one that's sort of obvious, I would say, or that's sort of easy is sort of property testing. So here's it's almost straightforward from what I just described to you. So let me tell you the question I have in mind. So consider the task of estimating the Schmidt rank of an n qubit pure state given many copies of this state. So like psi tensor m. We'd like to say that to do this with high probability, we need, to some accuracy, we need a huge amount of copies, right? And in fact, this was known before. There were lower bounds known before. It's not even hard to show, say super polynomial or even greater lower bounds on M. But what I think is sort of interesting about our result is that our result almost directly implies that we need super polynomial number of copies to get even a very coarse estimate of the Schmidt rank of a state, even when we're promised that psi has an efficient description, okay? And the proof of this is like essentially one line from our results, exactly what we did. We said let F be our maximally entangled PRS and G be our low entangled pseudo-random state. Well, then they have very different Schmidt ranks, right? But at the same time, they have efficient descriptions, okay? So this is the simple one, the sort of one that follows directly from the work. There are other results that we have that are sort of very similar in spirit, but they're a little bit more complicated. So we have lower bounds on testing the number of copies for estimating various properties of the spectra of a mixed state with the promise that that mixed state has an efficient description. And even, I think more ambitiously, we have impossibility for efficient entanglement distillation protocols. So that's actually sort of cool. The idea is that, entanglement distillation protocol at a sufficiently high level is some protocol that takes some arbitrary entangled state on n qubits and then produces sort of bell pairs from them, EPR pairs. And by using pseudo-random states, we can actually have some stronger impossibility results than what were known for the amount of entanglement that you should be able to distill with an efficient protocol. Okay, actually, the reason we thought about this started with holography and quantum gravity. This is a lot to unpack in the last 2 or 3 minutes of a talk. But I can try to say very briefly what's going on here. So at a very high level, there's this very famous ADS-CFT correspondence, which is a conjectured duality between, a theory of quantum gravity, which we call the bulk in anti-de Sitter space, and a quantum mechanical system, which is which is a conformal field theory or a CFT. And the idea is that at a high level we would like to understand properties like observables on physical observables on one system by thinking about this duality and by understanding physical observables on the other system. We don't have that many examples of this correspondence that seem to work really nicely, but one of the nicer ones is that we think there's sort of a nice correspondence between the entanglement of the state in the CFT and some geometric property, some property of the geometry of the corresponding state in anti-de Sitter space. Like literally the entanglement of the CFT state corresponds to the area of some minimal surface in the anti-de Sitter space. And so what's sort of interesting about that is that our result is saying there are states whose entanglement is really hard to measure, right? But then this ADS-CFT correspondence is saying, well, but on the ADS side of things, the geometry, that entanglement corresponds to a specific, geometric quantity, and in principle, that geometric quantity should be easy to measure. It should be an efficient. You can write it as an efficient, efficiently measurable, observable quantity. And so what we're saying is, let's suppose we have a toy model in which pseudo-entangled states really can be prepared by evolution with the Hamiltonian of this quantum mechanical CFT theory. Well, then, since we could use the geometry of the corresponding ADS-CFT state, anti-de Sitter space state to distinguish these states, this dictionary mapping, the sort of duality between these two theories sort of must be very complicated. It must be hard to describe because, again, entanglement is something that you can't feel and geometry is something that we think we can feel. So the dictionary must be sort of obscuring some of this efficiency. Okay, let me quit by talking about some open questions. I'm happy to take a few questions because these are open questions I'm really interested in. This is actually, the first one is maybe what I'm most interested in. I think it's directly related to a question that was asked earlier about whether it was possible to achieve small entanglement over mini cuts. So what I'm asking is it possible to construct pseudorandom quantum states that have area law entanglement? One thing that we can't show this at the moment, and there's many reasons for that. One of the main reasons is that the low entangled states we've constructed don't really have a well-defined spatial geometry. So it's not really clear what we would mean to say that the entanglement entropy of a subregion of that state scales like the area of the state. So I think it would be really interesting to even prove a very similar result, even with respect to a single cut, but where you have like a really well-defined simple geometry, like a 2D lattice or something like that, and the state is defined on that. We don't have that yet. This is one of my favorite questions. I also don't have much idea. Could it be that sufficiently deep local but random 2D spatially local quantum circuits give rise to pseudo-random states? So what do I mean by that? So suppose I give you a polynomial number of copies of the output state of a randomly chosen circuit in 2 dimensions, but I don't tell you that I don't tell you what the description of the random state is. In fact, I don't even tell you that that's how I did it. I tell you that I either did it that way, either prepared the state that way, or I gave you a Haar-random state. Right? Can you tell the difference? In other words, can you sort of learn somehow from copies of this state that the state came from the output distribution of a random quantum circuit? I think this is a really interesting question, in particular because we're now in an era where we're actually preparing copies of this state. Like that's what the Google experiment does, for example. And so it would be super amazing in my estimation if we could then show that in fact these were pseudo-random quantum states, and we can actually get maybe some cryptographic usage from that. Okay, and then of course, more applications of pseudo-entanglement. That's sort of the obvious one. I'm going to stop there and take your questions.